is Junichi Horikawa, and this is the 21st episode for VEX for Algorithmic Design, and the topic today is about half-edge basics, which is one of the useful computational geometry concept to explain the edges on a mesh object. Now, normally when we say edge in computational geometry, which means a unidirectional edge, which could be, in this case, one of the edge can be seen on a geometry mesh. But when we talk about the half edge is the directed edge which has the directional information. And the direction of this edge is determined by the primitive and the order of the vertices. Let's say if you look at this face, one of the primitive in this geometry, you can say that it is constructed with the total three edges, and the order of the edge is clockwise, like this, if the normal is upward. Meaning the half edge that belongs to this face is going this way. And the half edge which belongs to this primitive is going this way. And the half edge at here belongs to this primitive is going this way. Now if you look at the primitive on the next or neighbors, for this one it has its own half edges which goes like this. And you can see that the edges that share, the half edge that shares the same lengths and the direction and the position of the points has an opposite direction compared with the half edge on the neighbor primitive, which indicates that if the face is connected with the other face like this, one of the edge that shares the same edge with the other primitive has the one direction, and the other edge on the other primitive has the opposite direction, like this one and this one. Same for all the other face edge direction. And if there's no neighbors to the face, like right here, then you only have one single half edge. And it could be possible that one of the face is the order of the half edge going counterclockwise if the normal direction of the face is facing on the negative direction compared to the neighbors. In this case, then the order of the edge will be counterclockwise. But most of the time when you're dealing with the meshes, the neighboring mesh should have the same or similar direction, the similar normal direction. So this kind of situation doesn't happen that much, but in some cases this would happen as well. And there's also a chance that you have like multiple faces attached to a single edge. In this case you have like 3 neighboring primitive. In this case, it depends on the normal direction. This could go in any direction as well for each of the face. But if you know the normal direction of the primitive, and then you'll be able to determine in which order it will going to create the direction for the edges, for the half edges. Now in VEX, half edge has its own numbers. Like say this could be 0, this could be 1, and this could be 2. And you can retrieve these half edge numbers by using several useful VEX functions. For example, you can retrieve the half edge numbers by determining the number of points. Like if you want to get the half edge 0, you can specify some functions to get the half edge between the point 0 and 1, and you'll be able to get this one. If you want to get the half edge numbers in between 1 and 2, then there's just a function for it. You can also get a number from a primitive number as well by using a primitive number as a input, you can retrieve one of the half edge numbers, and you can also get the next number or next number of the half edge. I guess in this case it should be like this. So if you have the edge number 0, half edge number 0, and the next half edge number you can retrieve as 1, and for the next one you can retrieve 2, and on the next one it becomes 0 back again. There's also a function to retrieve the equivalent half edge numbers. Let's say if you have a half edge numbers for the primitive 1, but say you want to retrieve the half edge number for the primitive 2, which is connected or sharing the edge at 0 for the primitive 1. So 0 is for the primitive 1 numbers, but for the primitive 2 it might have a different numbers for this half edge. But there's just a function in VEX to find out what's the shared edge using these numbers, and that could be like 3, this could be 4, and this need 5. So half edge could be really useful in order to find out the structure information about the meshes like this. And there are some useful practical usage for this one, so I'm gonna show you the basic functions you can use in order to retrieve those kind of information in VEX, and how you can use them to do specific kind of things like subdividing and so on. So let's get started by using a simple concept, using simple functions to get some half-edge informations. So I'm gonna start by creating a grid. Let's set the rows and columns to 2 by 2 so that you only have one primitive, and the order of the point is like this. So you have 0, 1, 2, 3. If you go to the documentation page on side effects about half edge under a VEX sections, you'll be able to see a basic information that I have just explained you, and also you'll be able to see some functions which is for the half edge. And the first function that I would like to use here is this point edge function. So let's go inside. And there's two parameters set for this functions. One to use a point number as an input to retrieve the half edge, which uses this point number as a source of the half edge, meaning the starting point of the half edge. Now the second parameter set is the more specific one. You can determine the source point number and the end point number, the destination point number, to get that specific half edge. Now what I'm going to use now is this first parameter set to determine the point number and get the half edge which belongs to that point as a source. The second one is a bit more peaky because it only works if you know the direction of the half edge goes from the starting point to the end point. If you just set the numbers in a different opposite direction, and if that half edge doesn't exist, then it will give you an error or give you a -1 as a result. For the first one, I think in most of the cases you don't get a -1, meaning you don't get an error message for this one. So let's try to use this first. Going back to the Houdini, I'm going to use the point wrangle. And let's name this point edge, edge, maybe 1. Okay. And what I'm going to do is to first retrieve the half edge for each of the point using its point number. So I'm going to create the variable called edge and use the function point edge at ptnum, which is the point number. Now let's check this half edge numbers by creating an attribute called edge and store the one that I've just created or retrieved to this attribute. Okay, let's look at the geometry spreadsheet. Going to the inspector geometry spreadsheet, and for each point Now you can see the numbers from 0 to 3 for each of the point. And this is the number of the half edge. Now for the half edge 0, which is at which we have retrieved the edge numbers at point number 0. The point number 0 should be used for the source number, the source for the half edge. So the destination point should be either 2 or 1. But in this case, the normal direction is upward. And since the edge goes clockwise based on the normal direction, I think the destination number, the point number for this half edge 0 is equal to 1. Now there's just a function to check that specific values. What's the destination number for the specific half edge number? So let's try to use that to check if that's correct. And if you go back to the list for the functions for the half edges, you see a function called hedge source point and hedge destination point. And for this hedge source point, it is to use to get the source point of the half edge, and the destination point, the half edge destination point, is to get the destination point of a half edge. So by using those two functions, you'll be able to get a source point number and the destination point number from the half edge number. So let's try to use this. Let's look at the source point first. So it's pretty simple. You just need to input the geometry number, the input number, which is in this case 0, and the half edge number, which we have retrieved using the point edge function. So let's go back and going inside a code. So let's try to retrieve both source point number and the destination point number from the half edge numbers that we have retrieved using the point half edge function. So int source point is equal to edge source point, and we're going to use the half edge as an input, and for the destination point we can use the function called dst point 0 hedge like this. And let's try to store this into an attribute and check those numbers. So source point and destination point. And going back to the geometry spreadsheet, and for the first one, we have a half edge equals to 0, and the source point is equal to 0, which we have assumed because we have used the point number itself for the source point for the half edge. So it should be the same for the this one and this one. The point number and the source number should be the same. Now if you look at the destination point for each of the half edge, let's say if it's for the 0 and the source number is 0, okay, and the destination number is equal to 1, so you can see that the direction of this half edge is going from 0 to 1 like this. Now at the point 1, the source point is 1 and the destination point is 3, so going from this one to this one. And for the 2, it's going from this point 3 to 2. Sorry, a bit of mistake. We have to look at number 3 for this case. So number 3 points going from the source 3 to 2. So that looks correct. And for the number 2, going from 2 to 0. So we have just looped through all the points in a specific direction, which is a clockwise direction, clockwise order, based on the normal direction of the primitive. It's also based on the vertices order on the primitive as well. Now this is just information, but this information itself is pretty useful because you can assume you can get the points in an order or edges in an order like this by using like this. There are many possible applications using this useful information. Now going back to the point hedge functions, I'm going to try to use the second parameter set this time. So in this case, you have to determine the source point number and the destination point number in order to retrieve the half edge. So let's try to see how this works. Okay, so I am going to create another point wrangle. Okay, in this case, I'm going to set it as a detail attribute so that it just works once. I'm only going to retrieve one of the edge from this primitive by setting the first point number, the source point number, and the destination point number. Okay, so I'm gonna name this point h edge 2. Okay, so what I would like to do is to try to retrieve the half edge numbers for this edge going from 0 to 1. So to do that, you can say edge 1 equal to point edge 0, and the second parameter you have to set is the source point number, which in this case 0, and the second point number is equal to 1. And let's check this numbers by creating an attribute, the detail attribute called edge1, and store this value that I have just retrieved using point hedge. Now going to the geometry spreadsheet, to the detail, you see a number called 0. If the number is more equal or more than 0, then you have successfully retrieved the half edge number, and if it says 0, then the half edge numbers, which goes from 0 to 1, is equal to 0. Now let's see if we do the opposite direction. Let's see if we want to retrieve the other half edge information going from 1 to 0. In this case, which doesn't exist in this primitive, which is because from 1 to 0, you're going counterclockwise in this primitive using this normal direction. So in this case, that kind of order doesn't exist in this primitive set. So if we try to retrieve that and set it as store this in an attribute like this, and what we'll get is a value called -1. And -1 means that we couldn't, or this couldn't find any edge number, half edge number, which goes from 1 to 0. So whenever you get this -1 value using point h edge, then that means there's no such half edge in that specific direction. So this function, this parameter set is pretty useful if you want to retrieve the half edge which shares with a specific set of points, in this case 0 and 1, and if you know the direction that goes from 0 to 1, then the function works well. But if you don't know which direction it's going for this point set, if you don't know whether the point goes from 0 to 1 or 1 to 2, then this might not be a good option to use. Now, if you don't know the order of the point of the half edge, then what you can use is this function instead. Instead of using a point h edge, there's a similar function called point edge, which you can use it to retrieve the half edge number using a 2-point set, which is similar to the point h edge, but the difference is that you don't need to think about the order. I mean, this could be a source or this could be a destination. It will just returns you the value which is not negative to -1. So if this function finds either of the direction, then it will just return you the one that it finds out. Okay, so let's try to use this one. I'm gonna name edge 3 and use point edge for 1 and 0. And I'm going to create an attribute called edge 3 and store this edge 3 edge 3 retrieved from this point edge function. And let's look at the result, and it will give you some value, which in this case 0. So it didn't give you a -1 because it finds out the half edge, which is constructed with a 0.1 and a 0.0, and the order didn't really matter for this one compared to the point h edge. So this could be more flexible in order to find out the half edge which is shared by 2 points, which could also be useful at some cases, especially if you don't know the order of the half edge. There might be some situations you want to check if the half edge that you have right now is valid or not, if it exists in the primitive set or not. And there's just a function to check if the half edge exists in the primitive or not, which is called h edge is valid. So let's try to use that. I'm going to use the attribute wrangle and connect with this, and I'm going to name this h edge is valid. I'm going to set the detail. Now the function that I want to use now is this one called h edge is valid. Now the parameter set is pretty simple. The first input is the input number of the geometry, and the second input is the half edge number. Okay, so this can check if the half edge which you have just entered on the second parameter is existing inside the geometry set or not. If it exists, then it returns 1. If it doesn't exist, then it returns 0. So let's check this out. In total, we have like 4 half edges here, so from 0 to 3. Okay, so if we let's first create an integer attribute for the detail, like valid 1, and use h edge is valid 0, like 2, which is bit in between 0 to 3. If you look at the geometry spreadsheet for the detail, it says 1, since the half edge number 2 exists in this geometry. Now if we try to check the number which doesn't exist in this geometry set, like 15, now what you get is equal to 0. Now, so you can use this function to check whether the half edge numbers is still existed inside the geometry or not. I mean, this might not be used up much in terms of the static geometries, but it's going to be really useful when you're doing the geometrical operation in a subsolver, so that each frame the condition of the geometry changes, and maybe you want to use this function to check if the half edge that was existed previously is still existing at the current state or not. That might be the situation you want to use this. Now the next important half edge related function that I want to show you is this h edge next and h edge prev. This is to retrieve the next half edge on the same primitive, and for the half edge next and for the half edge prev, you can retrieve the previous half edge numbers. So let's say if you're looking at this one and the half edge numbers for this half edge is equal to 0, and this is equal to 1, and this is equal to 2. Now if you say if you want to retrieve the next half edge value for this one, you'll be able to retrieve this next half edge, which is in the direction which is in the order of the clockwise order. If you want to retrieve the previous half edge direction for this one, which is in the counterclockwise direction, you can use the half edge h edge prev function to retrieve this one based on this position. And this function is pretty useful to retrieve the the order of the edges and the neighboring information of the edge as well, and the point as well. You can also retrieve the point order information out of this function as well. So there are a lot of useful things you can do with this information. So let's see how we can use this. Starting from a basic, I'm going to retrieve all the half edge for each of the point. So I'm going to use the point wrangle. And let's name this h edge, next, and prev. Okay. Now first of all, I'm going to retrieve the current half edge values for each of the point using the same point h edge function that I did here. Okay, so I'm going to just copy and paste this one, maybe the whole stuff, to this edge next prev. Okay, so if you look at the geometry spreadsheet, you'll be able to see a half edge numbers and the source and the destination for each of the point. I'm going to rename the attribute a little bit for the source and the destination. I'm going to name the source as h-edge underscore source and h-edge underscore destination so that it's being aligned like this. Now next thing I would like to do is to retrieve the next half edge numbers from the h-edge half edge that I have retrieved using the point h function. So in order to retrieve the next half edge numbers, the function you can use is called h-edge underscore next. And the first parameter is 0 because this is the first input. And the second parameter is h-edge, which you have retrieved here. And as a return value is the half edge numbers. So let's name this attribute or variable like next h-edge. Okay. Now I am also going to try to retrieve the source point of this next half edge numbers. So you can just do the same things that I did here. So I'm gonna copy this one. And let's put next to this. And for the source point for the next edge, I'm going to use this parameter or this variable right here to retrieve the source point and the destination point for the next half edge numbers. So let's see this in a attribute. So first I'm going to create a attribute called next edge, and I'm going to store this next edge variable as an attribute, and let's also have the next h-edge source from this one, and I at next h-edge destination from the next destination point number. Okay, so let's check this out. Going into the geometry spreadsheet. Now for the first point, we have a edge number 0, and the source number for the edge number 0 is equal to 0, and the destination point number is equal to 1. So this is the first half edge for number 0. Okay. Now if you look at the next one, the next edge, it says a edge number is equal to 0. Equal to 1, and the next edge source number is equal to 1, and the next edge destination number is equal to 3. So you can see that the next edge direction is going from 1 to 3 like this. So the first half edge was this one, and the next half edge was this one. So you can see that you have just retrieved the next half edge information, which is on the clockwise order destination by looking at this information, and for all the other points you get the same, the next ordered half edge if you look at it one by one. Now let's try to retrieve the previous edge number as well, same as we done here. Pretty much the same things that I'm going to do. I'm going to copy all these and paste it, and instead of using next, I'm just going to replace it with the prev. Okay, so the next prev, and the function that we're going to use is called hedge prev, and the parameter set is the same. Instead of getting the next half edge number, you get the previous half edge number in this case. Let's also change these parameter as set as well. Change this to prev h edge, prev h edge, prev, and prev. This one as well, prev h edge. This one to prev source point and prev destination point. Now let's check this out in a geometry spreadsheet. Now for the first one, we have now a prev hedge number which says it's equal to 3, and the source number for the source point number for the previous half edge is equal to 2, which is this one, and the destination point number. Now the source point number for the previous half edge is equal to 2, and the destination point number for the previous half edge is equal to 0. Now the destination going from 2 to 0, and so this is the half edge that we have retrieved using the previous half edge function from this original half edge. So you can see that it's on the counterclockwise orders direction. The next thing I would like to talk about how you can be able to retrieve the shared half edge from one of the half edge on one of the primitive. Let's say if you're looking at this half edge primitive, half edge numbers right here on this primitive, and you want to retrieve the half edge which shares the same edge, in this case this edge, and what you want to get is the number of this half edge, this one, and there's just a function to retrieve that. By using the half edge numbers, you'll be able to retrieve the other half edge which shares the same edge for the connected primitive. And it is pretty useful in order to retrieve the next primitive's information as well, like as a neighbor. So let's try to see how we can use this. Let's first create a basic setup by creating a grid again. In this case, in this time, we're going to set the rows to 2 and the columns to 3. So it looks like this. You have a edge on the middle, which is going to be the shared edge for this primitive and this primitive. The first thing I need to do is to retrieve the half edge numbers for this edge. Now to do that, we could look at this primitive, and if we think about the clockwise order going from 0, 1, 4, 3, the half edge numbers for this primitive could be a source point number equal to 1 and source point number equal to 4. So we can use the point h edge function to retrieve this specific half edge, which goes from 1 to 4. So let's do that first. I'm going to use the attribute wrangle, and let's change this to detail, and let's change this to h edge, next equivalent maybe 1. Okay, now I am going to first retrieve the half edge, goes from 1 to 4, which you can retrieve using the point h edge function, goes from 1 to 4 like this. Now let's check this, if this is valid or not. We can see, we can have this inside the attribute called hEdge. For the detail, and it says 1, so the number of the half edge goes from 1 to 4 is equal to 1. Okay. Now, in order to retrieve the other side's primitive, the neighboring primitive's half edge, which shares the same edge right here, you can use a specific function called point. No, it wasn't the point, but hEdge next equiv function, which is this function right here. hEdge next equiv. So if you go there, the parameter set is pretty simple. The first input is the geometry input number, and the second parameter is the half edge that you're going to use as a base. Okay, so in this case, this is the parameter that you can use to retrieve the shared or the next equivalent half edge numbers for the neighbor polygon. Okay, so let's name the next equivalent half edge numbers as hEdge next equiv using the hEdge next equiv function. hEdge, and let's store this value to a hEdge next equiv attribute. hEdge next equiv. Right. Now looking at the geometry spreadsheet, and it says 7. So the half edge, which is for this primitive, which should go from the point number 4 to 1, is the number equal to 7. Now we can check if the source number is really equal to 4 and the destination point number is equal to 1 by using a same function we did use last time, hEdge source point for the next equivalent edge numbers, and the destination using the hEdge destination point half edge equivalent, next equivalent. And let's store this as well into an attribute for the source and for the destination. Okay, and the source says it says 4 and the destination it says 1, so going from 4 to 1. So the next equivalent half edge for this primitive is going from 4 to 1. So it's still in counterclockwise, still in clockwise order. So that seems correct. An interesting aspect of this hEdge next equivalent, if you try to retrieve the next equivalent for this next equivalent for this equivalent edge or shared edge that we have just found out, what you get as the next equivalent edge, let's name this next equiv 2 using the same function, but in this case we're going to use the last found shared edge, and let's store this into a similar attribute name but with the 2. Okay, and going back to the geometry spreadsheet, if you look at the hEdge next equivalent 2, now this number equal to 1 is same as the hEdge 1. So for this primitive, the hEdge number was equal to 1, and for the hEdge equal to 1, the next equivalent number was 7. And for the half edge number equal to 7, the next equivalent half edge for the number 7 was going back to the next one, 1. So you can just going back and forth using the next equivalent functions to see all the possible next equivalent edges. Same for the next half edges as well. Like if this is the edge you're looking at, and this is the next half edge, and this is the next half edge, and this is the half next edge, then at some point the half edge will go back to the same numbers by going clockwise. So together with the next half edge information, together with the next equivalent half edge information, you'll be able to have tons of information. You'll be able to retrieve the valuable geometrical structure information out of the meshes. And this can be used for several purposes. And for the next stuff, I'm going to show you some exercises, how you can actually use them to create a specific, for specific applications, for specific practices. The first practice I would like to show you is how you can compute the dual mesh out of the input geometry like this. The dual mesh can be retrieved by checking each of the point as a center, okay, and looking at the connected primitive for each of the point. Now for this point, the connected primitive is these 6 primitives. For this point, you have 1, 2, 3, 4. For this primitive, you have 1, 2, 3, 4, 5, 6, and so on. And once you get the neighboring primitive information, what you want to do is to connect the center point of the primitive like this in an order. Like this, and like this, and so on. And as a result, the result you get out of these information is called dual mesh. You can now remove those edges and keep just the primitive that you have just created. This. And I would like to show you how you can create this kind of mesh network using a half edges. And the important aspect of this one, the reason why we're going to use half edge for this purposes is because you can use half edge to retrieve the order of the neighboring primitive for this point. The algorithm is going to be like this. First of all, you're going to use a point H edge to retrieve one of the half edge from this point. Could be this one. So let's say this is the half edge equal to 0. Okay. Now, what you want to do next is to retrieve the previous half edge numbers for this half edge is equal to 0. Since this for the order of this half edge is going from starting point to the end point like this, so the half edge for this one belongs to this primitive. Okay, meaning if you want to retrieve the half edge for this edge, then you're gonna use a prev, a h edge prev, which is this half edge. Okay. And by using this half edge numbers, let's say this is equal to 1, you'll be able to get the equivalent half edge for this primitive, which is in this order. and this could be like 2. Okay, so by having this information, you can go through all the primitive in the loop like this until the end. Okay, and for each of the primitive, you can actually retrieve the primitive number from the half-edge numbers with a specific function that I'm going to show you next. So if you could retrieve the primitive numbers, then you'll be able to also retrieve the center point of the primitive. And since you have those primitive number in an order like this, you'll be able to connect these all together to create one single connected polygon like this. In this case, a hexagon. So that's how you can create a dual mesh or dual network for each of the point. And by doing the same process for each of the point with the same algorithm, you'll be able to create a dual mesh. And actually, there's a node just for that in a Houdini, a pre-prepared a node in order to create a the dual mesh. So you don't really need to implement it by yourself, but as a practice of the half edge, this is a good exercise. So I would like to show how you can do that. Now, if you just want to get the result like as ASAP, then what you can do is to use the divide node and then use the option called compute dual, which will create the dual mesh that I have just explained in a single toggle. So if you just need the result of the compute the dual mesh, then just using this node is totally fine. But in order to understand how half edge works, how you can use half edge to create this kind of mesh network, and using point wrangle and half edge related function is a really good practice. So I would like to show how you can do that. Okay, so since we want to do the operation for each of the point on this mesh, in this case a sphere, I am going to create a point wrangle. And let's name this dual mesh. Okay. And the first thing I'm going to do is to retrieve the first half edge number for each of the point using the point hedge function that we have used. So hedge is equal to point half edge 0 pt num. Now for each of the point, let's say this is the first half edge that I have got for this point, and for this half edge it belongs to this triangle here. And what we're gonna have to do is to do a loop operations for all the connected primitive which connects to this single point. Now we know how many primitives are connected to this point by using a function like a neighbors or point prims. So we're going to use that to get the total number of the connected primitives at specific points and use that number to loop through all those primitives. And each of the iterations, we're going to retrieve the primitive number using the half edge information and the neighboring information one by one. Okay, so let's do that. First of all, I'm going to retrieve for each of the point, I'm going to retrieve how many neighbor points are there for each at its specific point. So I'm going to use the function like a neighbors to first retrieve, or maybe I can just get the count of the neighbors using a function called neighbor count. Okay, 0 at pt num. So this neighbor count is going to be same as the primitive numbers. So 1, 2, 3, 4, 5 is this is the point we're looking at. We have total 5 primitives. It's equivalent to the 5 neighbor numbers. Okay, so first thing we're going to do is to create a loop like this from 0 to maximum neighbor count. Okay, now first thing I'm going to do is to retrieve the the primitive number out of this edge number that I have retrieved. So I do have a half edge numbers right here, which goes from this point to this direction. And in order to retrieve the primitive number which is related to this half edge, you can use the function called a h-edge prim. So by using this parameter or this function, you'll be able to get the primitive number from the half edge. So this is also pretty handy. Let's try to use this to first of all get the primitive number. I'm gonna name this prim using half edge prim 0 h edge. Okay. Now from this primitive we can retrieve the center point. So by using a prim function for a p attribute at prim. So this is going to be the center of the primitive. Okay. Now that we have the center of the primitive, I would like to add it as a new point. So int new point is equal to add point at the center of the primitive position. Okay. Now let's see where it has been created. So you have several points being created like this. Now next thing you want to do is to do the loop. Since you're only looking at the single primitive right here, but you want to loop for 5 times for this point right here. Okay. Now to do that, you need to first retrieve. So if we are looking at this half edge going from this point to this point, then I want to retrieve this primitive number next, which you can retrieve by, this half edge number for this primitive. So in order to do that, we can use the function called h-edge prev. And I'm overriding the h-edge using the same this previous half edge previous information or half edge previous function because we're going to use this updated edge for the next iteration. Okay. And now that we have retrieved the half edge for this edge going from this point to this point, we want to go to the next primitive using this information by using the function called h-edge next equivalent. So I'm going to override this h-edge again using h-edge next equiv. And inside a parameter, you can use h-edge again as a parameter. Now you got the same edge but going from this point to this point, which belongs to this primitive. Okay. Now this is a operation that you want to do inside a single loop, and by doing this over and over again, the h-edge is updated and can be used for the next iterations. In the next iterations, this primitive is going to be chosen to add the new point, and in the next iteration this point and this point and so on, then you'll be able to get the loop of the points like this, going counterclockwise. Or clockwise in this case, yeah. Now, after you have retrieved those points on a clockwise order, you just want to, next thing you want to do is to connect all these points to create one single primitive, one single polygon for each of the point. So I'm going to create a empty primitive, like named as poly, outside the loop first, like using @prim as the poly type, and inside the loop, after we have created the point, we can use the @vertex to add the point into this polygon primitive like this. Now as a result, all the point should have been connected to create one polygon. It's a bit hard to see because it's inside like this. So now I think the polygon has been created. What we can do next is to remove all the unnecessary point after doing all those operations. So we can say remove point, remove the current point used as the guide. And voila, as a result, you get a dual mesh, just like you get out of this function, out of this node, like this. Now, all the points currently are disconnected, so if you want to retrieve exactly the same thing as this one, you also need to use fuse to merge all connected points. And now you'll be able to have exactly the same geometry. So 80 points in total for this one, and 80 points total for this one. Now seems like we have a bunch of unused primitives here for this one. For this one it only says 42, but for this primitive we have like 122 primitives, which is because we have only removed the point, but we also need to remove the associated primitive geometries as well. So to do that, we can first retrieve the number of primitives connected to each of the point using like a point prims at ptnum, and use the for each int prim we need to write like this. Okay, and we can say remove prim 0 pr 1. So we can remove the primitive, which is visually not shown, but it does exist like an invisible object. But now we have removed all the unnecessary primitive, and all the values right here, the number of points and primitives and vertices are same as the one right here. Okay, so that's how you can create a dual mesh using a half edge as a information. And the idea that we have just done here could be expanded for many purposes and could be really useful for computational geometry. So if you're into the computational geometry, if you would like to know more about computational geometry, knowing half edge is pretty essential, I think. Now in the next exercise, I would like to show one of the example using half edge to create a subdivision or a crystallized subdivision using half edge. Let's see how I'm going to do that. What I'm going to do is to say we have a connected polygon like this as an example. And for each primitive, I'm going to retrieve the center point of the primitive. Okay, and also for each of the edge on the primitive, I'm going to find out the neighboring polygon, which in this case, this polygon. And I'm also going to retrieve the center point of the next polygon as well, like this. And what I'm going to do is to get the source point of this edge, the shared edge for this primitive, which is at this point, and the center point and the original center point and connect all these points together to create a triangle like this. Okay, and if it's connected to the other primitives like this, you do the same operations for each of the connected primitive like this, and continue doing this for each of the primitives. So for this primitive, let's say you have a connection like this, you're going to create a triangle which connects this, and like this. And by doing this for whole connected primitive, if it's the closed polygon that you're going to use as an input, it's going to create a closed polygon geometry, which is in result you'll be able to create some kind of subdivided polygon out of an input geometry, which is a bit similar to what we have just done to create a dual mesh. But I'm going to show you one of another way to create this kind of subdivided computational geometry. In this case, we're going to start with a polygon for each of the polygon. Last time we have created from each of the point, but this time we're going to do this kind of operation from each of the primitive. That's kind of a difference. Okay. Now I am going to start by creating some interesting geometry like platonic solids. Let's try to choose something like dodecahedron. Could work for anything. We can change the geometry later on. I'm going to use the primitive wrangle to do the subdivision. Let's name this subdivide. Now we haven't used the function, but there's also a function to retrieve the half-edge number from a primitive as well, just like the point h-edge function. If you look at the list of the function related to the half-edge, there's just a function, it's called prim h-edge. So if you click that, it says it returns one of the half-edges contained in a primitive. So, I mean, a single primitive could contain multiple number of half-edges, and this will give you one of the half-edge which exists in that primitive. Now we're going to access all the half-edges by using the h-edge next functions, so by going one by one so that we can go through all the half-edge inside the primitive. So the first half-edge number could be anything. So this using this prim head h-edge is not a problem. Okay, so I'm going to use this. The parameter set is, first of all, the geometry input number, and the second parameter is the primitive number. So int edge is equal to prim h-edge at prim num. And at this point, we don't know how many edge numbers are there for each of the primitive. We're going to use the while loop to loop through all the primitive edges, primitive half edges, until it goes back to the same half edge numbers. So let's say this is the starting point. This is the starting half edge numbers. And we can look through all the half edges by using a half edge next function, so going clockwise, and at some point you're gonna go back to the same half edge numbers that you retrieved initially. So that's when you want to stop the loop. So for that purpose, I'm going to use a while loop. Okay, so also going to create a variable called start to store the initial half edge numbers. Okay, now I'm going to use the while loop. While, let's also check if it becomes negative, then we're going to stop the loop as well, which might not happen, but let's just say we have this kind of condition here. So while the half edge is not equal to -1, then it keeps looping. But we do need to exit this loop at some point, so we need to have the same condition first when we're going to exit this loop. And this loop, this condition could be when the updated edge or the current edge, half edge that we're looking at is equal to a start, and that's when you want to exit the loop using break. Now we're going to update the half edge using the function called hEdge next. So hEdge next for 0 hEdge. So by using this, you'll be able to, if the current hEdge is this one, then the next hEdge will become this one, and the next edge will become this one in the next loop, and this one in the next iteration, and this one next iteration. And once you have the same number for the updated hEdge and the start, the initial start, which is this condition, then the loop will exist. And yeah, I think it's working. Now, now that the basic loop constructor is made, or structure is made, we're going to use, we're going to retrieve some necessary information to create what I have explained in a sketch. So the first information we want is the center point of the original primitive, which you can retrieve by accessing to a at p, which is pretty simple. Okay, now I'm going to create a new point here. So I'm going to name this as cpt1 using add point 0 pos. Okay. Now, next thing I would like to do is to retrieve the primitive which is on the neighbors, the neighbor primitives, and also the edge information. We would like to retrieve the source point number as well. Okay, so in order to do that, we can retrieve that using from the half edge information right here. Okay, so if we have half edge information right here for this primitive, let's say this goes from this point to this point in this direction, in this clockwise direction, we can first use the next equivalent function to retrieve the half edge direction goes from this one to this one for the neighbor polygon. Okay, so let's get that. I'm gonna name this edge is equal to edge next equiv 0 hEdge. Okay. Now that we have retrieved the half edge which belongs to this primitive, we now can retrieve the primitive number using this hEdge number, half edge number. So int n prim is equal to hEdge prim that we have used in the previous exercise as well, using the half edge numbers. Okay, now now that we have a next primitive information, we can retrieve the center point of this primitive as well. So let's retrieve position 2 is equal to point, a primitive 0p at n prim, and we can add a new point at this point position as well. Okay, so we have a point set. Now the next thing we want to have is this point information, which is the source point of this hEdge, or a destination point for the equivalent equivalent half edge. Either way is fine. I'm going to use the source point from the original hEdge. So we can get that by saying let's say source pt is equal to h edge src point at h edge. Okay. For this point, we don't have to add a new one because it already existed. Now that we have three points in total, CPT1, CPT2, and SRCPT. So we're gonna combine all these points to create a one triangular mesh. So let's do that. I'm gonna name the primitive as tree and add prim0. The type is poly. And we're going to go clockwise by going from CPT1, CPT1, and this one is SRCPT and CPT2. Okay. And now something has been made, but we cannot still see it because we have these primitives blocking our view. So and the last, we can remove all these primitives using remove prim. Voila, you have now just created a subdivided geometry out of this input geometry, like a crystal shape. And if we changes this shape, like cube or a tetrahedron, octahedron, any shape could work if it's if the polygon is connected. Okay, even for a soccer ball. Maybe not for the teapot because this is not a polygon, I think. Okay, so like this. I mean, you could also try to see for other geometry like torus, and you'll be able to have this kind of blocky shape or crystallized shape, which could also be interesting. Okay, so that's how you can use a half edge from a primitive to create this kind of a subdivided geometry. As you might be able to imagine, you could use it for a recursive shape like a fractal crystallized shape as well. Okay, that might be also an interesting topic as well. Okay, I'm going to use the switch so that you can switch between the geometry. All right. Now in the last exercise for the half edge, I'm going to try to create a bevel for input geometry. So meaning I'm going to first pick all the corner points out of the input geometry and create a bevel like this. And trim out these corner like this. So for each of the corner points, we're going to first create this red triangle shape using some ratio information, how many distance are there from the corner, like using t. Okay, so that you can control the value, how much the size the triangle could be. Yes. Now after you have created a triangle, you also need to create the inner geometry, inner polygon as well. And for these, we can create that for each by using a primitive wrangle to look for each of the primitive. Now for each of the corners, we can use point wrangle, and for those faces, we can use a primitive wrangle for each face for the input geometry. So in this case, in order to create this kind of a beveled shape, we're going to do a separate operations, one for the corner and one for the faces. And by combining all together, we'll be able to create this kind of beveled geometry. So that's the last example I would like to show you. But if you understand what we're going to do now as an exercise, I think you are almost, you are just ready to go using a half edge for any of your purposes. Okay, now, so let's start by creating a simple geometry like cube. And we're going to deal with the cube first. And we can try out to see if this same function works for a different geometry as well. Okay, so as I said, we're going to deal with the corner and for the faces. We're going to start from the corner points as well to create a triangle using half edge as an information. Okay, so point wrangle. Let's name this corner bevel. Oops, bevel. And then so the first thing I would like to do is for each of the point, I'm going to search for the initial point, initial half edge numbers, which you can do that by using a point h edge that we've been using for a lot of times. Okay, and just like we did for the dual mesh, we can count the neighbor of this at this point, so that how many loops we should do in order to get the order of the the connected primitive, so that we can retrieve the edges in order to create this kind of triangle shape based on the information of each of the edges position. Okay, so to do that, currently the point is connected to 3 neighbors, and we can retrieve how many points are there by using neighbor count function again. And we can loop through this count number like this. This time what we want to do is to retrieve the point position for the first point, which is same as the point position of the current point wrangle. So for the source point, we don't really need to get the position, but for the destination point, we need to retrieve it by using the half edge destination point function. So let's do that first. So int dst point is equal to hedge dst point at hedge that we have retrieved right here. So as a result, you'll be able to get the destination point for the first half edge, which could be this point if we are looking at this point as a starting point. So if the half edge direction is going this way, then we're looking at this primitive. Okay. Now, after we have the point position or point numbers, we will be able to get the point position as well. So dst pos is equal to 0.0 p at dst pt. Okay, now that we have the source point position, which is equivalent to the original point position right here, the center point position right here, which is equal to at p, and we also have the destination point position, we'll be able to get the point in between those 2 point positions. So we're using some ratio value. So let's create a position value, a custom position value, starting from the current point position and creating a vector going to a point position, destination point position from a current point position multiplied by some ratio between 0 to 1. Let's make this ratio. You'll be able to control the point position from this point to this point, from 0 to 1. Okay, now that we have this point position information, we can add a new point. So int npt add point 0 pos. Okay, now if we show up the point, we can see, okay, the point is moving right here. So I guess this was the first edge for this point. It's a bit hard to see, isn't it? Okay, I think we should let me make the point size a little bit bigger. Not this one. Okay, the point size is determined by, where was it? I guess this one. Yeah, it's a bit hard to see, but there's a point right here. And it's moving based on this slider value, so I think it looks fine. So this is the first half edge. Okay. Now, what we want to do now is to change or update half edge after we have created the single point for a specific half edge. So for the next iteration for this loop, we want to update the half edge to the next connected half edge. If we are looking at this one, then the next primitive or next half edge that I would like to get is this half edge numbers right here. Okay, so to do that, like we did last time, we first going to use a half edge previous to retrieve the previous half edge numbers for this primitive. If the edge is going from this way to this way, this point to this point, then the previous half edge is going to be this half edge, going from this point to this point. Now we're going to retrieve that first. So h edge is equal to h edge prev 0 h edge. And then, since the half edge is still belongs to this primitive, we want to change this half edge belongs to this primitive next. And to do that, we can change this, but we can use the half edge next equivalent so that we will be able to have the edge goes from this point to this point for this primitive. So h edge is equal to h edge next equivalent 0 and h edge. Okay, and by doing that, you can loop through all the neighbor count, all the edges, using the neighbor count as a total number of the loop. And so in this case, in total, you have 3 points being created for each of the point and each of the corner points. Now you want to add the primitive, you want to create a triangle connecting all those points. So I'm going to create a poly at prim outside the loop as the polygon type, then use add vertex to add newly created points into this polygon like we did last time. Okay, now the corner point is not necessary anymore. We can delete that by saying remove point at btnum like this. So now we have just got the corner triangle like this. Now I think there's still a empty primitive is existing in this things right now, so we could also delete that like we did last time. We can just go back here, where was it, this one, and use the same function right here to remove all the empty meshes as well, like this. So now we have like 8 primitives and 24 points for these cubes. Okay, that looks good. If it's 0, you have a total, you don't have any corners or triangle. If it's going upward, at 0.5 it connects with all the other points. So let's limit this ratio to 0.5. So this is going to be the maximum. And the next thing I would like to do is to create the face part. Now to do that, I'm going to go back to the cube, and this time I'm going to use the primitive wrangle to do a similar operations but for each of the primitive. Okay, and I'm gonna name this like face. face bevel. Now for the faces, what are we going to do is that for each of the faces we don't really need to retrieve the neighbor informations, but we can just look inside a single primitive, but we still do need the order of the point or the edges. So what we can do is to first retrieve the half edge numbers out of this primitive. Any half edge number should be fine. Something like this edge. Let's say we have this, retrieve this half edge right here, goes from this point to this point in a clockwise order. Now, by using a half edge next, you'll be able to get the next half edge and the next edge and the next edge, and in total, in this case, 4. Okay, and by looping through all those edges, for each of the edge, you'll be able to get the source point position and destination point position, and by using the same ratio we used right here, we'll be able to get the point right here and right here somewhere in that 30% position, and for each of the edges. And using those position that we have retrieved, we can connect all those points to create a face polygon. Then we can just combine this point and this primitive and this primitive together to create a one whole beveled geometry. So that's the plan. Okay, so the first edge we can retrieve from the primitive. We can use the same function we used last time. It's called prim hedge at 0 prim num. Okay, now I am going to use another while loop. So I'm going to create a starting from the hedge number, and while the hedge is not negative and hedge is updated using the hedge next 0 hedge, and if the half edge is equal to start, meaning if we have go back to the same half edge numbers at some point, then that's when you want to break this loop. Okay, so that's the basic structures. Okay, now I am going to write some code here to retrieve the information from each of the edge. Now the first information that I would like to get is the source point position and the destination's point position for each of the edge. So you can use a hedge source point to retrieve the source point number and destination hedge dst point 0 hedge to get the destination point number, and then you'll be able to get the position as well for the source and destination using point 0 p at source vector source destination position point 0 p dst. Okay, now we also need the ratio, how much we should move the corner point to inward direction. So let's have this ratio value from the parameter. Maybe we could give this outside the loop. Okay, and this value here, this ratio here, can be connected with this value. So I'm going to copy this parameter and then paste using paste relative reference to link the value, so that by changing this value we'll be able to change this value as along with it. If we change this one, then this value will change as well. So let's retrieve the point position by moving this point to the right direction, this point to the left direction using this ratio value. Okay, so for the source point, I'm going to name it as a say position 1, and position 1 can be starting from the source position and using the vector going to a destination position from a source position multiplied by the ratio. So that's going to be the position 1, and the position 2 is going to be a destination starting from the destination position and then source position minus destination position to create the directional vector multiplied by a ratio. So you'll be able to get the point which goes from this point going to the left side using this ratio. Okay, now we can create a point at each of the point positions. So I'm going to use add point 0 position 1 and pt2 at point 0 position 2. I'm adding the position 1 first, which is at the source position, which is based on the source point position, is because we are going to create the primitive in the clockwise order. Okay, so if we want to create the primitive in the counterclockwise order, then we should start creating the points from the destination point, and we also need to use a hedge previous instead of the next, so that we can retrieve the previous half edge numbers so that we can go counterclockwise. But in this case, we're going to create a counterclockwise, we're going to create a clockwise ordered polygon or vertices. So the order to create the point is like this. Now we have created the 2 points for a single edge, and in the last we have in total 8 points for the single square polygon. So in order to connect all those points together to create a single mesh, we're going to create a primitive outside the loop as an empty polygon first. Add prim 0 poly, then use the add vertex to add those 2 points. So add vertex 0 to poly pt1, add vertex 0 poly pt2. Okay, now we do see some silhouette here, so now we can remove those primitive that we don't need anymore. So remove prim num1. Okay, now we have created the face without this bevel triangle. Now we have this triangle corner here and we have this face here. All we need to do next is just combine these together to create a combined mesh like this. Now if we, at this point, if we change this shape, this parameter here, we can change the how much bevel we want for the corner like this. By using the same idea, you also be able to create the edge bevel as well. Or so if you want to try, please do as an exercise. Okay. Now, since all the points are being disconnected right now, we can, in the last, we can use the fused to merge all those disconnected points to create it as one single object like this. Okay. This. Okay, and what's interesting about this is that this operation can be done recursively, because this function could work for any kind of geometry. Let's try with other kind of geometry, shall we? I'm gonna create a null node in between the geometry so that's be easier to switch. So let's also try with the platonic geometry first. a platonic solid. Okay, now what I would like to show you is changing those geometry by cube. Octahedron gives you icosahedron, gives you this kind of interesting geometry. Like gives you like something like a soccer ball already, or a dodecahedron. It's very interesting. Yep. And one more thing I would like to show you in the last is that this operation that we have built here could be done recursively. So after we have done this shape or the bevel setup, we could do another bevel setup by copy and paste, connect it to this one again for the next operations, and continue doing that. Now we can skip copy and paste by using this for each loop. And let's set this to fetch feedback each iterations, and fetch feedback, so that this will create a feedback loop. So I'm gonna connect this one right here, and then I'm going to connect this one right here. Okay, now let's set the count a bit smaller, because if it goes 10, then it's going to be too much subdivisions. Now you can see that by changing these numbers, you can iteratively apply the same operation again and again. Like this. Interesting, isn't it? So let's set this 4 and change this value here. It's kind of interesting shape happening. Right. So I'm gonna end this up by changing the color of each of the primitive based on its area, I guess. So I'm going to calculate the area using the measure node for each primitive, and use the attribute promote to retrieve the maximum of the area for each of the primitive, and set it to detail. Change this to max area to retrieve the maximum, so that in detail we'll be able to see a maximum. Oops. I think I need to set area here, so that we have a max area being applied. And then we can use the color node to use all those information to color the primitive by its attribute. So color primitive, the attribute that we want to use is area, and from 0 to the maximum inside a detail. So / add op input zero, and the name of the attribute is called max area at 0 position. Okay, now we can change those colors, like maybe the blight is blue, going down to green and orange, and then red. Something like this. Okay, and by changing its shape, you can see a bunch of different subdivision results in a colored way. Okay, we could still create a switch node. switch between the geometries. We could also try with torus as well, like give a torus. And this gives you a bit more brighter, interesting pattern. I like it. And if you change those sliders, you can change the bevelness of each faces. At the end, it will just create a square. Alright, so that's what you can do with the half edges. And the information that I've shown you today for the half edge is pretty basic one, and the operation or the exercise that I've also shown is also a pretty basic operations, but by understanding all those processes that I've explained, you can do a whole bunch of computational geometry, which seems to be really difficult previously, but makes it more easier by understanding this useful structural information. So I hope you get something out of this and be able to use it for your own purposes. And the next topic I would like to talk about for this series, VEX for algorithmic design, is the remapping. Remapping a value into another values, and I would like to show you a bunch of techniques and tips and tools for the remapping. There are a bunch of useful techniques here out there, so that's what I want to show you with several examples and several exercises, which could also be really useful for a procedural modeling or motion graphics and so on using VEX. Okay, so that's it for today. Thank you very much for watching, and if you liked the video, please like and subscribe to the channel. And I have also started the Patreon page myself, so if you find those videos useful, I would appreciate if you could support me to continue creating those videos. Okay, thank you very much, and I'll see you next time. Bye.